So big idea 3 is about chemical reactions, energy changes, and redox reactions. So essentially what we're looking at here is how matter changes. And the way that it changes is that atoms get rearranged or reorganized, or electrons get transferred and moved between atoms. And this allows us to see different phenomenon, which we can determine to be different types of reactions. We can measure how much energy is released or gained, endo-exothermic, and we can do quantitative measurements through redox potentials, through stoichiometry, etc. So the first main category we're going to focus on today are just types of reactions. So types of reactions. This should be pretty quick review, but one that we need to know is a synthesis reaction. Synthesis reaction is when two atoms or molecules are combined to form one. So something like A plus B turns into AB. Two separate atoms or molecules combined to form one new one. The opposite of a synthesis reaction is a decomposition reaction, where you have one compound like AB which decomposes, gets broken down into A plus B. Third type of reaction is combustion, and this is when a hydrocarbon, so CXHY, where X and Y are variables, is combined with O2 gas, burning, to form CO2, carbon dioxide, and water as products. So this is always combustion reaction. We have to have a hydrocarbon. Remember, a hydrocarbon is just a molecule with only carbon and hydrogen in it. Fourth type of reaction is a single, we'll just do double displacement first, where two atoms switch what they are bonded to. Usually occurs in redox reactions, so we'd have something like AB plus CD. Atoms, usually the cations, positive charges, rearrange based on their activity levels to form like AD, AD and CB. We can also have a single displacement, which is the same idea, but there's one atom that starts off by itself. So A plus BC. Let's say the metal element A is more reactive. It's going to displace element B to form AC plus B. Again, these are the two types of reactions we usually see that are associated with redox, transfers of electrons, which is the next category we need to know, redox. This is when elements gain or lose electrons, so something like A2 plus gains 2 electrons to become A with a neutral charge. We need to know about acid-base reactions. If we take an acid, not based, no little b here, HA plus BOH, when we combine an acid and a base, we always form two of the same products, water and a salt, an ionic compound with a metal and a nonmetal. And last but not least, we need to know about precipitation reactions, when a solid product is formed. So this would be something similar to AB plus C, both aqueous, turn into AC solid plus B. With precipitation reactions, we need to know our solubility rules. So what compounds will never form precipitates? Compounds with group 1 metals and ammonium ions will always be soluble. They will never form a solid precipitate. And also compounds with nitrate, NO3-. So if you see any of these three types of elements or polyatomic ions, you know that that compound will not form a precipitate. No solid formed if it has those present. So let's get into these reactions a little more carefully. We have to know how to what we're going to see a lot of is drawing models. So an example of a particulate diagram is, let's say we have the compound K2CO3, potassium carbonate, and we drop it into a beaker of water. And then we zoom in and we want to see what are the ions floating around. Well, we know that carbonate is a polyatomic ion, so that's CO3 2 minus, and we're going to have K plus and K plus. We're going to have two of them. So if we looked into a beaker where this solid compound had dissolved, we would see the ions of K plus, and CO3 2 minus in a 2-to-1 ratio. We also have to be able to do particulate diagrams with, let's say you added K2CO3 plus say we did MgCl2. And we knew that this formed a precipitate, like magnesium carbonate is a precipitate, and we have 2 KCl's. If we wanted to draw what the particulate diagram would look like at the end, since this is going to be a precipitate, again, I'm just going to tell you that, at the bottom, we would expect to see a layer of magnesium carbonate, CO3, and floating around would be our spectator ions. So we'd have K plus floating around and Cl minus floating around. And then depending on the stoichiometry, the ratios of these, we might have more potassiums or more chlorides, depending on how many moles of each we have. But being able to interpret, draw, and analyze these diagrams is a big part of the AP curriculum this year. How can we measure energy changes associated with these? Well, one main way is through enthalpy. So enthalpy is abbreviated delta H. Okay. The measure of the essentially energy either gained or transferred, basically the energy change, remember delta means change, in a reaction. So we learned two vocabulary words. We learned about endothermic reactions and we learned about exothermic. Endothermic reactions occur when heat is absorbed, and this usually occurs when bonds are broken. Okay, think about a carbon-hydrogen bond. In order to break this bond, we have to add some energy to it because it's stable otherwise. An exothermic reaction is the opposite. It's when heat exits, when heat is released. This is when bonds are formed. Okay. And this is when delta H is a negative number. This is when delta H is a positive number. Remember, the way we calculate delta H is the enthalpy of the products minus the enthalpy of the reactants. So we can draw two diagrams that represent these if we have time and energy. Let's say here's the initial potential energy of the reactants. We know we're going to have to add some energy in order to make the reaction start, and then we end up down here. This height is called the activation energy, the energy needed to get those molecules to form the transition state, at which point they can react to form a new compound. Since this is the initial energy, basically we can call this enthalpy of the reactants. And down here is the final energy. This is our enthalpy of products. Delta H, since this value is much lower than this value, let's say this is like 10 and this is 100, delta H for this reaction would be this distance, this difference right here, this red, which would be our products minus reactants, 10 minus 100, which gives us a negative value. So when the final line is below the initial line on an energy diagram, you know that is an negative delta H, which means it is an exothermic reaction. On the other hand, if the initial energy is here, we add some energy and then the final reaction coordinate is up top, this delta H is going to be greater than 0 because let's say since this value of the product's enthalpy is higher, let's say it's like 100 and this is 50, delta H is now going to be products minus reactants, which is 100 minus 50, which is equal to 50, which is greater than 0. So this would represent an endothermic process. So we got to be able to know how to recognize these two diagrams. For endo and exothermic reactions, you need to know if heat is absorbed or released, if enthalpy is greater than or less than 0, and if bonds are being broken or formed. Last thing we also need to know is catalysts, how catalysts work. So if this is the reaction energy, first check yourself based on this diagram. Is this an endothermic or exothermic reaction? Well, since the final energy value is lower than the initial, we know that delta H is going to be less than 0, so this is an exothermic reaction. If we added a catalyst to it, what that does is it changes the height of the hill. It makes this hill smaller than it was initially. So now, by adding a catalyst, what we've essentially done is we lowered the activation energy. So we're going to increase the rate of the reaction. So we might see, you might be asked, okay, given a reaction diagram like this, something like that, what effect would adding a catalyst have? What would the diagram look like? Let's say adding a catalyst causes there to be two transition states. What would that look like? Well, now we would want to have something that kind of looks like this. We have to have two little hills. So we have to be able to interpret these diagrams in multiple different ways. Okay. When electrons are transferred between atoms, we have a redox reaction occur. Remember, this stands for reduction, oxidation. Oxidation. And remember, a reduction reaction is when an atom gets reduced, it gains electrons. When an atom gets oxidized, it loses electrons. And the best way that we've learned to remember that is oil rig. Remember, oxidation is loss, reduction is gain of electrons. Got to know those terms inside and out. And the way we figure this out is we assign oxidation numbers to elements. Okay? Few basic rules. When elements are in their standard state, the oxidation number is 0. So for example, if we have Fe solid, that has an oxidation number of 0. If we have O2, that has an oxidation number of 0, since O2 is a diatomic molecule, it's in its standard state. Other examples of that are N2, H2. All of these have a oxidation number of 0. We also need to know, just in general, how to add oxidation numbers for compounds. So for example, let's say we had CuSO4, copper sulfate. Well, copper is a transition metal, so we don't know what its oxidation number is immediately. Oxygen is always 2-, so -2 times 4 is -8. So therefore, sulfur, if sulfate, you got to remember, is a -2 charge, 2-. So if oxygen is -4, sulfur must be +6, and therefore copper must be +2. So then that means, let's say a reaction happened and you were left with copper plus something else. So now, since copper has an oxidation number of 0 in its standard state, it went from having a +2 oxidation number to having an oxidation number of 0. So its charge went from positive down. It has a lower charge, which means it must have gained electrons. So we would say that copper, in this case, got reduced. We got to be able to recognize that if we're given a whole reaction and figure out what element is getting oxidized or reduced. So for example, let's say we had the reaction of iron and hydrochloric acid, 2HCl, which is going to produce iron chloride, FeCl2, and H2. figuring out which elements got oxidized and reduced and writing the half reactions. Well, how do we do that? First, assign the oxidation numbers. Iron, standard state, 0. Chlorine, halogen, -1. Hydrogen, always bonded to a nonmetal, +1. Chlorine, -1. Iron needs to be +2 in this case because there's 2 chlorines. And hydrogen is in standard state, so it's 0. So let's track which elements changed their oxidation number. Chlorine didn't. It stayed -1, -1. Iron went from 0 to +2, so its charge got bigger. So it must have lost electrons, so it got oxidized. And on the other hand, hydrogen went from +1 to 0. It got lower, its oxidation number, so it got reduced. So writing the two half reactions, well, for iron, it would be Fe goes to Fe +2. So to balance out the charge, we need 2 electrons on this side. Since they're a product, that means they were released, they were lost, which supports oxidation. And then for hydrogen, we have H+, 2 of them, going to H2. So to balance out the charge, we need 2 electrons on this side. And you could double check if you add these reactions together. What do you get? Do you get the original reaction? Yep, heck yeah, you do. These electrons would cancel. If they didn't, you'd have to multiply them by a coefficient, and et cetera, et cetera, et cetera. We can quantify redox reactions by measuring reduction potentials. Okay, reduction potentials would be found in a table, E0 values. Okay, so for example, the reduction of zinc 2+, Zn2+, if it gains 2 electrons to become pure zinc, we can measure the voltage that this would create, and this creates a voltage of -0.76 volts. Since this is a negative value, okay, E0 is less than 0, this is non-spontaneous. Zinc 2+ will not just get reduced by itself. There would have to be a stronger reducing agent in order for this to occur. Okay. In order for it to be spontaneous, we need E0 to be greater than 0. And we can do that by mixing 2 half reactions together to get E0 of the cell. And remember, E0 of the cell is calculated by measuring E0 of what is getting reduced minus E0 of what is getting oxidized. And the way to remember that is just kind of the word redox in order. This usually occurs in a galvanic cell, which is just like a battery. Okay. Remember the setups of these. We have, one compound over here, voltmeter, another compound here, stick in a solution of that same compound but in its salt form, and then there's a salt bridge which allows us to maintain neutrality. Labeling, remember the anode is where oxidation takes place. The cathode is where reduction takes place. Simple way to remember this is anox, red cat. Okay, anox, red cat. Anode is oxidation. Reduction is where the cathode happens. Anode is where oxidation happens. Reduction is where the cathode happens. We also need to know the opposite of galvanic cells, which are electrolytic cells. The purpose of an electrolytic cell is to take a voltage that is negative, so less than 0. That's non-spontaneous, but we can make it spontaneous by passing a current through it. Okay? And so we saw this when we took water. We passed a current through it to make oxygen gas and hydrogen gas, and I know that reaction is not balanced. This reaction does not occur spontaneously, but by adding a current through, we can make it occur spontaneously to separate the two elements. We can then quantify that using the equation we learned for I equals Q over T, okay, where I is our current in amperes, okay, T is time in seconds, and Q is charge. Okay. So an example of where this occurred is, let's say we run a 2.50 ampere current through iron 3 chloride, FeCl3, for 15 minutes. Okay. And we want to know how much iron is going to be produced. Okay. Well, we know if the initial time that took place was 15 minutes, we know that the current amperes of units would be 2.50 coulombs per 1 minute. We know that from Faraday's constant, 1 mole of electrons has about 96,500 coulombs. This is, remember, Faraday. It's on your equation sheet. And we know from the equation here, Fe is going to be, there's going to be a positive 3 charge, so there's going to be a transfer of 3 electrons. So this is going to have, for every 1 mole of Fe that's produced, that's going to involve the transfer of 3 moles of electrons. And we know that 1 mole of Fe has a mass of about 55.8 grams. So if we do the stoichiometry here, and we do all the math out, we'd be left with about 7.23 times 10 to the negative 3 grams of Fe. So we did these problems a few weeks ago, relatively recently. The only other thing that I have not covered in this video is stoichiometry. And we'll just do a ton of stoichiometry practice by using molar mass to convert from grams to moles, doing limiting and excess reagents and reactants. If you need a review on that, there is a video from earlier in the year you can watch, but we'll do a ton of practice with this material on Monday.